So, good afternoon all. This is session 10 and this is Syed Mohammed Mustaq. So far we have discussed the mechanical properties and thermal properties in session 9. So I guess the total mechanical properties is completed and we are left with thermal properties in this session, and also the electrical and magnetic properties also we discussed, and I will not totally explain everything, but I will make sure that whatever I am going to discuss will be helpful in solving the assignment problems or whatever doubt. It will even clarify your doubts too. Okay, so without any further ado, let me see whether I'm recording. Yeah, it is recording. Without any further ado, let's start. So this is session 10. So what previously we have discussed? We have discussed the thermal properties, right? So in thermal properties, first we mentioned about the melting point, right? So at first, just a second. I started with melting point, so let me start with melting point. Melting point nanoparticles, right? So for example, if I have a solid particle like this, quite clearly, so I have a solid particle like this, and suppose there is a small liquid that has been formed, and this is my thickness T. Then how we are going to approach this problem? So as I've said before, I'm not going to derive everything again, so I'm just going to write the initial part, okay, so that you people can understand. So what are the things that we should need to write? We know that delta G total equals to delta G bulk plus delta G surface, right? So delta G bulk plus delta G surface, and we know delta G bulk is L delta T by T naught into V. We are talking about volumetry, and the surface that came into picture is, let me write it, delta G surface, that is equal to AL gamma L. This is my liquid, this is my solid, AL gamma L plus ASL gamma SL. See, ASL gamma SL is the interface, right? The interface between the solid and liquid, minus AS vapor gamma S vapor. It's not vapor, it's just a gas, so I'm just representing it as a V. So we can write here LV and LV here. Won't make much difference. So one is from liquid minus solid plus this is surface one. So for equilibrium conditions, again we need dou delta G total by dou T equals to 0, right? That's what we came into picture. Now let me add one more slide. So let's take, as we are talking about sphere, So that will turn out to be L naught T naught minus T divided by T naught equals to 2 gamma SL divided by R minus T. Now what happens for T tends to 0, if we apply limit, then T melting point, actual melting point for a radius R will be equals to T naught of 1 minus 2 gamma SL by surface energy, no, not surface energy, sorry, it's not surface energy, it's the melting, enthalpy of melting times R, the radius. So upper melting temperature for spherical particle or the melting temperature for a spherical nanoparticle decreases with decreasing particle size. So it should look like temperature, particle size will look like this. So this is my actual bulk melting temperature. It will approach like this. Now what happens if my nanoparticle is embedded in a matrix, right? Then what happens? So let's write, suppose what happens if my nanoparticle is embedded in a matrix? Then let me write, this is my surface, and suppose if I have a liquid particle here, right? Then this is, suppose this is my surface, this is liquid, and this is gaseous form, right? So this will become my write it again. Suppose this is my liquid, then if this is my for example, this is my solid, this is my liquid. This is my solid and this is my liquid, and this is interface between liquid and vapor, right? So LV, and this is between gamma SV. Now balancing, and suppose this is the contact angle, or you can say this is the angle which makes with the surface is theta. Then upon balancing it will turn out to be gamma SL cos theta equals to plus gamma Sm gamma SL cos theta equals to gamma S. Gamma Lg cos theta equals to gamma SL equals to gamma SV SG. Now the wetting property depends upon these three functions, or gamma Lg, the surface free energy between the liquid and gas, and the surface free energy, the surface energy between solid and liquid, and surface energy between solid and gas. So if our gamma SL is greater than gamma L, if gamma Sm is greater than our gamma Sg, then the melting temperature of nanoparticle should be lower than the bulk temperature. And if our gamma Sf is greater than gamma Sg, then the temperature of the nanoparticle should be greater than bulk melting temperature, or higher than that temperature. So we can even substitute and see what exactly happens, right? We will even substitute. We will even substitute and see how we get this relationship. It's not that complex, but rather simple equations, simple algebra anyone can solve. Okay, so this is where we ended our last session. So we told that how the melting temperature is decreasing with the particle size. No, it is only for pure metals, not for alloys. So this is the relation. Here we have pure gold, pure lead, pure copper, pure bismuth, and pure silicon. With decreasing the radius, or decreasing the size of the particle, the melting temperature decreased. Moving on to the next one, which is the thermal properties, where we are discussing about the last part, where we discussed about the thermal conductivity. Thermal conductivity arises from two parts. One is from electron transport, other is from phonons. Electron transport can be explained by kinetic theory of gases. If you are talking about metals, and if you are talking about semiconductors, it will change. Now, this is for electrons. Now coming to the phonons. phonons are collective oscillations of atoms. Phonons are collective oscillations of atoms. Right? Suppose if I have one-dimensional lattice, vibration in one of the atoms leads to stretching and minimizing of bond length, and this result will be shown in all the parts of atoms. Right? So, for example, if this atom is displaced from its inset position, then it will look like this. Right? So, we can simplify this problem as a spring ball problem. For example, the forces. This is our initial position, x0, and this is the position it has moved, x1, and this is x2 and x3. Now we can write the mass balance or the force balance equation, like F equals to ma, F B0 equal to minus kx, and ma is m times dou square x by dou t square. And here we can solve the problem by, sorry, it's still the thermal properties, not electrical properties. Still, I'm talking about thermal properties, right? So this is how the phonon motion results in the transportation, or the helps in the conductivity part. Right? Now, coming to how exactly it happens. See, if we see here, this is the temperature, this axis. This axis is my temperature, and this axis is my thermal conductivity, right? So increasing temperature will have the more vibration of atoms, so more oscillations of atoms. We'll have more like the high frequency of oscillations of atoms, which results in higher thermal conductivity, right? So even upon that, if we are thinking about the nanoparticles, for example, the thin films, right? So if we are talking about the thin films, then we know there are like 0 dimension, 1 dimension, 2 dimension, 3 dimension nanoparticles, right? So if you're talking about 2-dimensional nanoparticles, you're only considering the phonon conduction, right? Conductivity from phonons. Then what happens? So, as we know, the phonons are the collective oscillations of atoms. So, if I have a thin film, and if I have another thin film, 2 or 3 thin films, then what happens? So there is a scattering, because in this thin film there are one type of atoms, right? So one type of ball spring, right? But this is number 1, and this is 2. This may contain different types of ball and spring model, because the spring is nothing but the bond energy, right? Or you can draw it from potential. Well, it looks like this. Potential energy in terms of R. So this part we are considering about this parabolic part, even though it is not perfectly parabolic, but if we assume that this take the parabolic part, then this is our equilibrium position, and it can be seen as a harmonic oscillator also, right? So, and depending upon the potential energy, the depth, this bond energy will be defined. So this thin film has different atoms with different bond energy, which turns out to, if we assume it as a classical problem, it will be a different spring constant, and this thin film has again different thing, right? So if we have a thermal conductivity, the heat is transferring from here to here, and if At the interface, we have these phonon scattering, right? Because of the change in the atomic orientation and also the atomic species that came into picture. Now, that's all about phonons, and it's a rather vast topic. So we will stick to the electron transport rather than going to the phonons one, because it involves many complex mathematical equations. So I do not want to discuss here. Let's just move to electron transport. So now, coming to electron transport is the motion of electrons, right? Where the electron will collide, electron will move from one point to another point and collide with another electron. So that way the energy is being transferred or carried away from one point to another point. That's how the heat is being transferred from one point to another point. So coming to that one, so now what are the two things that are dealing with here, right? So one is our quantization. Quantization for electrons. Now, why we have this? If we are talking about electron transport and the quantization for electrons, it will come into picture if we are talking about the dimensionality of nanoparticles, dimensionality of nanomaterials, right? So why? We will discuss more briefly how the quantization and how it depends upon the what about the quantization in the electrical properties. But let's just briefly let's just do with this quantization. Right? So quantization is nothing but restricting the energy levels for any quantum particle. Right? Here the case is electron is a quantum particle. Then we are just restricting the amount of energy levels that the electron can take. So if I am talking about 3-dimensional, and for that again we have to discuss a bit of pieces about the density of states, and I even discussed in previous class, but let's just again do them here. So this is my density of states and this is my energy, so it will look like this, right? So it is a smooth curve. The electrons can occupy different energy levels from here to here. There is no restriction or anything that electron cannot take this energy value, right? So that's how it is. And then coming to the 3-dimensional particle, so there is no restriction, right? Now coming to 2-dimensional nanomaterial. Now 2-dimensional nanomaterial, for example, if I take a thin film, it has a thickness in nanometers. So this dimension there is a quantization of electrons, right? So the electrons can freely move in x and y direction, but so in 2-dimensional nanomaterial, the electrons can move freely in x and y direction, but they cannot do the same in the z direction. Why? Because of the quantization in the z direction, right? So that is again one of the properties. So for example, if I take the 1-dimensional nanomaterial, for example, if I take CNT, so its circumference, this area x and y is quantized. So but not in the z direction. So electron can freely move in the z direction. As I said before, the electrons move ballistically in this direction because they can freely move in one direction, but they cannot move in take values or take the energy values in x and y direction. So and that one and we have a zero dimensional quantum dots, where in all three dimensions the energy levels are quantized. The electrons cannot freely move in three dimensions, right? So that is about quantum dots, and yeah, that's all about the electron transport discussed. Oh, yeah, that's all about the electron transport, how the electrons movement, the collision of electrons between the adjacent electrons will turn into the conduction, and the other one is the phonons, right? So these are the two ways, two major ways from which the conduction of heat takes place. So let's just again do a brief recap. In the phonon conduction at nanoscale quantum confinement, so discretization, the quantization, the quantum confinement, and the classical scattering effects takes place. In bulk homogeneous non-metals, like wavelength of phonons is much smaller than the length scale of the microstructure, but in nanomaterials, the length scale of structure is similar to the wavelength of phonons. So the scattering decreases. The scattering intensity decreases, right? And the other one is because of this decrease, or the discretization, sorry, not the discretization, and so because of this reduction in the dimensionality, so there is a leading to the quantum confinement. And again, the presence of nearby surfaces like 0D, 1D, 2D microstructures causes change in phonon frequency. That's why we have the scattering that takes place. Because the velocity of variations in wave amplitude changes. Again, so if you want to more discuss about how the velocity of variations in wavelength amplitude changes, we have to consider the group velocity. And group velocity is nothing but the collection of, like, for example, if I show you here. So group velocity, see, one is we have a standing wave. Standing wave is nothing but the wave amplitude and frequency is not changing with time. But the other one, which is a traveling wave. In traveling wave, when we are considering, we have a group velocity. We are saying about group velocity. Here we have different waves that are superimposed with different frequencies, different wavelengths that are superimposed, and they result as a wave packet. Inside it will look like this. Right, it looks like a wave packet, and when we see it with respect to the time, it sees as a moving from one point to the another point, right? So that is about this. And the phonon lifetime, so not the photon is the light particle, right? So the phonon lifetime is modified due to the phonon interaction with free surface and grain boundaries, if you are talking about the alloys. Now, the 0D structures has a phonon bottleneck because phonon cannot transport, and one-dimensional nanomaterials behave as a phonon waveguide, right? Because the phonons cannot substantially move from one CNTs to another, so they have to move in this direction. So it acts as a phonon waveguide, right? Now, coming to, for example, for CNTs, the thermal conductivity is 3000 watt per meter Kelvin, right? So two-dimension radiation shielding, wear resistance, thermal barriers, and flat display panels, photovoltaic application, etc. So that's all about the thermal properties. Now coming to the electrical properties. Now the electrical properties arises from two parts. One is coming from quantum effect, and another one is coming from the classical effect. Oh, I shouldn't say the classical effect, but that can be more explained classically. That's why I'm mentioning the classical. Right. So what do I mean by quantum effect? Quantum effect is nothing but, just I have mentioned before, the quantum confinement of quantum particles. If we have, if we are talking about zero dimension, two dimension, one dimension, two dimension nanometers, because one of the dimension is less than 100 nanometers, right? So there is a quantum confinement in those materials. Right? So coming to that, so we have zero dimension, one dimension, two dimension, and three dimension. So to understand these effects, let's first start with the density of states. Right? So if we start with density of states, then it will be easy to understand or see with a picture what exactly is happening. Right, so let me start with zero dimension, one dimension. Let me start with zero dimension, right? So, yeah. Let me start with let me start with density of states so that people can easily understand. Yeah, that will tell about the quantum effects. So the electrical conduction of electrons in systems considered large in size compared with the nanoscale. Right? In this case, the conduction of electrons is delocalized. So it's again, if you localize an electron, it's against the uncertainty principle. So also in metals, we are considering delocalized electrons, like the electrons can freely move inside the material. For example, this is my bulk material, so electron can freely move in this bulk material, right? So now, as they travel their path, the electrons are primarily scattered by various mechanisms, such as phonons, impurities, and interfaces, resembling a random walk process. So, however, as the system length scale is reduced, or if the system, like the dimension, one of the dimension is reduced from like 1 mm to a few nanometers, like less than 100 nanometers, then the system scale is reduced to the nano scale. The two effects come into picture. One is a quantum effect, where due to electron confinement, the energy bands are replaced by discrete energy states. So I will come to the density of states in just a few minutes. So leading to the quantum effect, where due to electron confinement, the energy bands are replaced by discrete energy states, leading to cases where conducting materials can behave as semiconductors or insulators, and to the classical effect, where the mean free path for inelastic scattering becomes comparable with the size of the system, leading to the reduction in scattering events. Right? So in 3D nanomaterials, the three spatial dimensions are all above the nanoscale. So in 3-dimensional nanomaterials, the three spatial dimensions are all above the nanoscale. Therefore, the two aforementioned effects can be neglected. However, bulk nanocrystalline materials exhibit a high grain boundary area to volume ratio, leading to increase in the electron scattering. As a consequence, nano-sized grains tends to reduce the electrical conductivity. In the case of 2D nanomaterials, with thickness of nanoscale, quantum confinement will occur along the thickness dimension. See, so if the dimension gets, if one of the dimension, like here it is 3 dimension, but here it is 2 dimension. Here the thickness is getting reduced below 100 nanometers. In this case, the 2-dimensional nanometers with thickness at nanoscale has a quantum confinement occurring along the thickness dimension. So simultaneously, the carrier motion is interrupted along the plane right? So along the plane, the carrier motion is interrupted, because if you have like 2 or 3 layers, then of different materials, then there is the interruption along the plane of the shape. In fact, as thickness is reduced to the nanoscale, the wave function of electrons are limited to very specific values along the cross section. This is because only the electron, sorry, uh, yeah, the only electron wavelengths that are multiple integral of thickness will be allowed. That I will be showing in a few seconds. Now. Yeah. So the electrons become trapped in that, right? So decreasing the dimension of the nanomaterial will have the discretization of energy levels, which will trap the electrons in that dimension. But trapping is nothing but allowing the electrons to only those certain energy levels, but not to the other energy levels. But that's not the case in the other dimensions, which are not in a nanoscale. So let's start with the quantum effect, right? So first, let's see what is the density of states. How do we define, or how do we so how did we get this function, right? So density of states function, right? So coming to that, see, for example, if this is my three-dimensional particle, like three-dimensional system, so let's say it is a cube. All sides it has length L, like this is length, and this is my breadth, and this is my height. So every side it is in length L, and electrons have the momentum K. Right? So we represent momentum. It's not a momentum; it's a wave number. So we represent momentum is equal to hk, right? H cut k. So let's say the momentum has a momentum p with wave number k. Then in the Fourier space, it looks like. Okay, a few more slides. So in Fourier space, that will look like. Fourier space, that will look like dots. And all these k values lie inside a sphere, and this sphere is called as Fermi sphere. All the k values of electrons will lie inside the sphere, right? So we are not applying any magnetic field. So if you apply magnetic field, and this sphere will turn out into a cylinders, and all the energy states will lie on the surface of the cylinder. Let's not. It's again a different topic. Let's not go very deep into that. So let's say there is no magnetic field. B is equal to 0, and all the electrons lie inside the sphere. All the electron energy states lie inside the sphere, right? So now again going to the density of states. Now number of states available per unit volume with an energy E. That defines our density of states. Now let me write it. Number of states available per unit volume of energy E. Right? So, and if I represent this function as gk, then gk dk will be equals to 4 pi square 4 pi k square dk. This is the surface area of the sphere times the thickness, right? So if I take a sphere of a thickness dk, now the volume occupied by one state, right? So that will be given by the volume occupied by one state. All the states of electrons are represented here, and they are represented as 2 pi by divided by 2 pi q by LQ. Now this is just a Fourier transform, right? Fourier transform 2 pi q by LQ. Now again coming to the density of states, as I have represented before, number of states available per unit volume, right? So the number of states gk dk divided by the volume of each state, right? That is equals to volume times 4 pi k square dk divided by 2 pi whole cube. Now we know energy is represented as P square upon 2m, and I have represented before what is P. P is equal to h cut square k square by 2m. You can represent h cut square or h square by 2 pi square, but h cut square is also said as the reduced Planck's constant, because the h value, h square value is getting reduced, so it's just spelled as a reduced Planck's constant. Now again, what is k square? Now everything we have to represent in terms of E, because we want everything in terms of the real space thing, right? So in terms of energy values. So what is k square? K square will be E times 2m by h cut square. Now what about dk? Upon differentiating, this will turn out to be h cut square by 2m whole power 1 by 2 e power minus 1 by 2 times 2m by k square times d. Upon differentiating, this is the value you will get. It's simple. First you differentiate it, it will become 2k dk, right? And this dk will k will go that side, so you will have a dk value, and yeah. Now substituting this dk value in this equation, so let me write it. What was that value? 4 pi by 2 pi whole cube k square dk, which will be equal to 4 pi by 2 pi cube times 2m h cut square e 2m by h cut square minus 1 by 2 e power minus 1 by 2 d. And this whole thing can be represented as how? Ge dE, right? Instead of gk dk, we can write it as Ge dE, or density of states represented in terms of energy values, not k space, right? Now this Ge will be equal to upon, let's see, yeah, 8 pi by, I'm not simplifying it because again it will take time, so I'm just writing it whatever the equations are. So 2 power 1 by 2 m power 3 by 2 divided by h cut cube and e power 1 by 2. This is all the constants. This is the mass of the electron, this is reduced Planck's constant, this is pi values, and these are constant values. So G of E is proportional to e power 1 by 2, right? And if I represent it in the graph, this is exactly a parabola, right? So yeah, here you illustrate, so this is how it looks like. parabola. Right? Now this is for the 3-dimensional material. Now what about the 2D? Right? For 2D, it becomes the surface. Now what happens with the surface? If we are talking about the surface, then that will become to, let me write it again. Now that g of k dk will be equals to what? Circumference 2 pi k dk. Instead of volume, it will turn out into area. So 2 pi divided square times L square. If I am just representing in terms of area, that will turn out to be L square. Now again, going back, and let's just do the problem. Let's cut square k square by 2m, then k square will be 2me by h cut square. Again, what is k? K dk 2m de by h cut square. What is dk value? We know k is equal to root of 2me by h cut square. Now 2m by h cut square times de into equals to k equals to root, right? It's not, it's divided by root 2me by h cut square. Now this will be equals to, and because we have 1 here, so 2m h cut square whole power 1 by 2 and e power minus 1 by 2 times de. So this is what it is. Now substituting this, here we will finally arrive to the equation GE will be proportional to e power z. G is proportional to e power constant. Then how does our graph look like? Our graph will look like this. Our graph GAD, and this is the density of states. Graph will look like, let me show you how does it look like. Yeah, it will look like this. This is how it looks like. It's constant. Where our GED is constant. It doesn't depend on the energy, E values. Right? Now going on to for one-dimensional materials. For one-dimensional nanomaterials, now that surface now will become aligned. So our GK dk will be just dk divided by 2 pi by L, because we are only considering a one dimension, right? So This is how it looks like. Now again, going back to that decay equation, dk is equals to h cut square by 2m whole power 1 by 2 e power minus 1 by 2 de. We substitute it there. Then it will simply be turned to ge is proportional to e power minus 1 by 2. And again, how does our density of states graph will look like? It will look like this. It look like a spikes in the density of states. Now, if again we can even do, if we try to do that for z-dimensional nanomaterials, there will be total discretization, and there is no continuous form. There is total just a discrete energy levels. For zero-dimensional nanomaterials, right? We show them here. That's how the density of states take place. Now again, going back to what are the density of states, what does it mean? So it means that these are the energy values that are allowed for electrons that can be in a material. For example, if I take a single hydrogen atom, these are the energy levels. So the discretization takes place. Right? So there is 1s orbital, there is a 2s orbital. Like first orbit has a certain energy of electron, the second orbit then across a certain energy. There is no overlapping, or there is no continuous energy values. Right? So that is all with the density of states. Now coming to the quantum confinement, right? So how for now we know what are the density of states, right? So moving on to the quantum confinement, right? How assign these, if we have a quantum confinement in any dimension, now how we are going to assign the values for the electrons, like energy value for electrons. For that there is a simple way. For example, if we take the particle in a box, for example, for a one-dimensional box, let's say this is my box, this is a one-dimensional box. Now again, why we are discussing this? Because only electron wavelengths that are multiple integers of thickness will be allowed. All the other electron wavelengths, now what is the wavelength? Wavelength of electron. Wavelength, we know the energy of a particle, of a quantum particle, is given by h, right? What is the h? H is a Planck's constant. Nu is a frequency. It may be the frequency of electron, it may be the frequency of photon. In this case, the frequency of electron. Now that frequency will depend upon the wavelength. Now our wavelength will define our energy, right? So yeah, going back to the electron wavelength that are multiple integers of thickness will only be allowed. All the other electron wavelengths will be absent. In other words, there is a reduction in the number of energy states available for electron conduction along the thickness direction. The electrons become trapped in what is called the potential well, right? That's why we are talking about the particle in one-dimensional box, right? So this is where the theory comes from, like the electrons become trapped in what is called as a potential well. So this is a potential well of width equal to the thickness. This is width equals to the thickness, right? In general, the effects of confinement on the energy for a two-dimensional nanomaterial, the thickness at nanoscale can be written. For two-dimensional, three-dimensional, zero-dimensional can be written. For now, let's just assume for one-dimensional, right? One-dimensional discretization. For example, in 2 dimensions, there is a one-dimensional discretization or one-dimensional quantum confinement, right? So that will be equal to, let's derive it now. We know we are deriving for the two-dimensional nanomaterial, right? So yeah. Now the particle in a box, or let's say this is our potential well. Here the V is 0. Let's say this is our, next slide, yeah. So this is our potential well, a particle. Let me write it again. A particle in a one-dimensional infinite potential well of dimension L, right? So our length is equal to thickness of the two-dimensional nanomaterial. For example, if we are talking about a thin film, so that is its thickness, and that is equals to L. The potential energy is 0. So let's write our assumptions. The potential energy is represented as a V here for now. So V is equals to 0. The conditions are 0 less than x less than L, right? And V equals to infinite if x is less than 0 or x is greater than L. Now it's these are very basic assumptions, and we assume the walls have an infinite potential energy to ensure that the particle has a 0 probability. Now again, what is the wave function? If we square the wave function, then that will give us the probability of finding that electron there, right? So if I represent any electron with the wave function psi, then if I normalize it, or if I square it, will tell you the probability distribution, or the probability of finding the electron at particular position, right? So we assume the walls have infinite potential energy to ensure that the particle has 0 probability of finding being at the walls outside the box, right? So psi is 0. Let me write that too. Psi is 0 when V is equals to infinite. Now psi has some value when V is equals to 0, right? Doing this will significantly simplifies our mathematical calculations later. So as we employ now, these are our boundary conditions, right, are represented here. Now let's solve the Schrodinger equation. What is our Schrodinger equation? It is a very known equation. Schrodinger equations have two terms. One, the kinetic energy term. Now this is my kinetic energy term. Square. Another one is potential energy term. And also our wave function is a time independent, right? We are not considering the time, because again it will bring complexity while solving our equations. So it is a time independent Schrodinger wave equation. Time independent wave equation. So that will be equals to, one is a kinetic energy, potential energy, that will be equals to energy of sound, right? And this is the energy operator, that is equals to the kinetic energy term and the potential energy term, right? So again, we are not we are just considering only one particle, and if we have an excitation energy, that will add some value here, not exchange interaction, not excitation energy. If we are considering 2-3 more electrons and we have some potential energy values, if we have some potential energy, then again this will bring more complexity, so we are not even considering that. So our exchange interaction term will be 0, Again, we are considering the potential energy, as we are considering in between. Potential energy is 0 between 0 to L, x is between 0 to L, potential energy is 0. So this wave function can be simplified to h cut square by 2m dou square psi x by dou x square equals to energy times psi of x, right? So how does it look? It looks like this: dou square by, it's a linear differential equation now, equals to 0, right? And we know the roots: a1 sin x ax plus a2 sin bx, right? Or cos bx. Let me write it here. So the solution will look like this: a1 sin ax plus b1 cos bx. So this is my equation. So I write y of x, right? So for this, that will turn out to be, now let me rearrange it. Now, even assuming a constant, my constant k is equals to, we know what is k. K will be equals to e to m by h cut square. This is our k. Well, em by h cut square, right? So let me write it as it. Let me denote it as a k square. Now, upon solving, seeing the from deriving from this will turn out to be psi of x is equals to a sin kx plus b cos kx. Now again, the boundary conditions. Considering the boundary conditions, the solution to the Schrodinger equation we found above, we found here, right? We found here is the general solution for a one-dimensional system. Now we need to apply our boundary condition to find the solution to our particular system. And according to our boundary conditions, the probability of finding the electron at x is equal to 0 or x is equal to L is 0. Let's say, let's not make it equals to, let's remove this. At x is equal to 0 and x is equal to L, so wave function, our wave function dies, that will be 0. So when x equals to 0, for boundary condition 1, at x is equal to 0, psi equals to 0, right? So psi of 0 equals to a sin 0 plus b cos 0. Because psi of 0 is equal to 0, we had this first boundary condition. So 0 equals to a times 0 plus b. So b equals to 0. So we do not have any constant now. We do not have any constant. So our final wave function will be psi of x equals to a sin kx. Now we can solve for constant a. Now let's differentiate the equation. Dou psi by dou x equals to ka cos kx, right? And again, doing differentiation, double differentiation will turn out to be dou square psi by dou x square equals to minus k square a sine kx, right? Since, and also we know psi equals to a sine kx, this will again turn out to be dou square psi by dou x square is equals to k square psi, right? Now upon writing k, what is k? K is equals to 8 pi square me by h square upon 1 by 2. So if we plug this k into our wave equation, this psi will be equals to a sine 8 pi square me by h square whole over 1 by 2 into x. Now when x is equal to L, this wave function will be equals to a sine 8 pi me by h square into L. So this is our boundary condition 2. And now this psi is equals to 0, right? Because at x is equal to 0, our wave function dies, or we do not have any probability of finding our particle there. So sine, our amplitude cannot be 0 because we are considering the wavelength as it has a wave characteristics. So only thing that can be 0 is the x term, and we know that sin x, when sin x can be 0, so x can be integral multiple of pi, then we can clearly say that sin x can be 0. So what is our x here? Our x here is 8 pi square me by h square, not the reduced Planck's constant, 1 by 2 times L equals to n pi. Now where is equal to n, 1, 2, 3. Putting this back into our equation, that will turn out to be psi equals to a sine n pi by L into x. Now to go for a, we have to integrate it again. Integrate, we know the probability distribution. From 0 to L, we have the total probability distribution is 1, right? So integrating will give me 2 by L. Just a simple equation can do it. So substituting there will be equals to psi equals to 2 by L sine n pi by L into x. And please know this is a standing wave equation, not the moving, right? The moving or the wave packet. So this is just a standing wave. Now how to find the energy levels, right? So energy levels will be given by the allowable energy levels, right? The allowable energy levels will be given by En equals to n square h square by 8mx square. Now what does it show? The energy of the particle is quantized, right? Because in the density of states we have seen for the three-dimensional particle the energy is continuous, but not here. Here the energy is quantized, right? Now what are the possible values? The lowest possible energy of the particle is not 0, because this is called the 0 point energy. and it means the particle can never be at rest because it always has some kinetic energy, right? This is also consistent with Heisenberg uncertainty principle. If our energy of the particle is zero, then one either our position or wavelength gets infinite, right? So that's a violation of the Heisenberg uncertainty principle. Now again, what does this mean? What does n equals to 1 and n equals to 2 mean, right? Again, that is our question. So for n we have like this, and for n equals to 2 we have like it just shows the probability distribution, right? This is our wave function, and when we do the psi square, right? So it tells me the probability or the wave function distribution, right? Where the probability of finding the electron and the probability of finding a particle at a certain spot in the box is determined by squaring psi. We have psi and we squared it, so the probability distribution for a particle in a box at the n equals to 1 and equals to n equals 2 looks like this. Now, the number of nodes, the places, what do I mean by node? Again, where the places where the particle has the zero probability, right? So this is my node and this is my anti-node. So increasing with the number of nodes where the particle has zero probability of being located increases with increasing the energy, right? Because the more number of nodes will be added. For 0, for 1 here and here, for 2 we are at extreme positions and middle, and for 3 we have 2 positions and 2 extreme positions, totally 4. So as the energy of the particle becomes greater, the quantum mechanical model breaks down as the energy levels get closer together and they overlap, forming a continuum. Just what happens in this, the three-dimensional particles, the density of states is like this. So this continuum means the particle is free and can have any energy value. At such energies, the classical mechanical model is applied as the particle behaves more like a continuous wave. Therefore, the particle in box problem is an example of standing wave. So how we get the standing wave, and also an example of wave particle duality, right? And so that is about the density of states and the quantum confinement, right? So for a two-dimensional nanomaterial with thickness at the nanoscale can be written as the quantization will turn out to be En equals to pi square h cut square by 2 ml square into n square. Now n square represent the discretization in which dimension. For example, this is a z direction, right? If this is my thin film, this is my z direction, right? So this is in z direction, and for other x and y direction it will simply be p square by 2n, right? So if I represent E total for two-dimensional nanomaterial, so the two-dimensional nanomaterial, the E total will be px square. So 1 by 2m px square plus py square plus, and this is equals to 1 by 2 ml square. You can take out pi square h cut square and that's this is our total energy. And L, what is L? L is the width of the potential well, and for if you are talking about electrons which revolve around the nucleus, so N is the principal quantum number here, and the basic assumption we took was the infinite depth potential well model. So and this is these two terms are for the unrestricted motion of electron. So let's assume the let's assume the z direction to be the thickness direction, and x and y in plane directions in which electrons are delocalized, right? So there is no localization, just I mentioned before, there is no discretization of energy levels, right? So in x and y direction we have delocalization of electrons. So under these conditions, the unrestricted motion can be characterized by two wave vectors. Instead of representing the px or the momentum, we can represent px as the momentum or the momentum operator as px square is equal to h cut square k square. Now representing that will be as E unrestricted, right? The unrestricted motion or the delocalization will be equals to h cut square k square by 2m plus h cut square ky square by 2m. Now E unlocalized will also can be represented as kf square, and where x and y are directions, so the energy corresponding to these delocalized electrons will be given by this, and it's also called the Fermi energy, which can be represented like this. Now the total energy of an electron, finally representing the total energy of electron in two-dimensional nanomaterial is given by E of n equals to pi square h cut square n square by 2ml square plus h cut square kf square by 2. Since the electron states are confined along the nanoscale thickness, the electron momentum is only relevant along the in-plane direction, right? And also, as a result of, for example, if you are talking about the scattering by phonons, and impurities occurs mainly in in-plane, leading to 2D electron conduction. However, for 2D nanomaterials with nanocrystalline structure, the large amount of grain boundary areas. We have grain boundary areas, and also we have interfaces, right? So that can lead to more electron scattering or phonon scattering. So which decreases the electrical conductivity. And in case of one-dimensional nanomaterial, let's talk about one-dimensional nanomaterial. In terms of the one-dimensional nanomaterials, so quantum confinement will be along x and y directions, right? So if I represented the total energy of electrons will be equal to pi square h cut square by 2 ml square. If I assume a cube, that will be equal to mx square plus ny square plus h cut square kz square by 2m. This is for one-dimensional nanomaterial. Right? For example, if we are talking about CNTs, and if I represent for zero-dimensional nanomaterial, y square x cut square by 2 mp x square y square and u square. And there is a discretization in all three directions, on all three dimensions. So, and because of that, we have the discretization of energies. So, coming to here. And because of this, we have the discretization for the zero dimension nanoparticles. And because the electrons have to jump from one energy level to another energy level. So if we are talking about the density of states, we have this conduction band and this valence band. So for the conduction of electrons, the electrons would jump from valence band to conduction band. But in three-dimensional materials, it is easy because the energy levels are continuous. But for the zero-dimensional nanoparticles, we can make, because of discreteness, we can even create the insulators from metals. Why? Because of the spread of energies. There is no like continuous motion. The electrons have to jump from one energy level to another energy level. There is no availability of energy levels for electrons. Right? So that is another one. And these two-dimensional, three-dimensional materials are used in circuits, for external circuits as electrodes. For 2D and 3D nanomaterials, the ohmic contacts are possible. However, for zero-dimension and one-dimension nanomaterials, the contact resistance between the nanomaterials and the connecting plates are usually high. So, thus one mechanism of providing conduction is through electron tunneling. This is another quantum mechanism, quantum mechanical mechanism where in infinite potential well, I have said before that the wave function of finding the wave function is 0. From 0 to L. From 0 to L we have wave function, and from after L before 0 we have 0 wave function, or the probability of finding the electron is 0. But it is not actually the case. The quantum particles actually tunnels from the barriers. So we still have the wave function, even though it is dying very fast, which is an exponential. It is an exponential term, but still the wave function exists after the potential energy. It means the wave function doesn't drastically vary. So this is again the quantum tunneling is a quantum mechanical effect in which the electron penetrate potential barrier. So for an electron to tunnel from one metal to the another across an insulator, one of the metals, one of the metals must have the unoccupied energy states. So a simple way of achieving is to apply the voltage across a circuit to raise the Fermi energy, right, of one of the metals. In this fashion, electrons can tunnel from metal with highest Fermi energy to the metal with lowest Fermi energy, producing a current I in the circuits. So let me show you how it looks like. So suppose this is my metal, this is my insulator, this is my metal, this is my metal, 1, 2, and I am applying the voltage here. So if I raise the Fermi energy, then the electron can tunnel from one to another. So that is where they are used. Even this is the electron tunneling can also be used to develop field effect transistors, right? FETs made from quantum dots. So these can be used in also for the dielectric behavior. A large number of grain boundaries in nanocrystalline materials is expected to increase the dielectric constant. Right? For example, nanocrystalline Ti2 has a higher dielectric constant, so compared with coarse grained samples. This is due to a reason. Under an applied electric field, the positive and negative charges are segregated at the interface and will lead to some form of polarization. So these are the different applications for 0 to 3-dimensional nanomaterials in different cases. Now moving on to the magnetic properties of the nanomaterials. So the magnetism arises from moments, right? The magnetic moments. Again, where how these magnetic moments have certain value. So magnetism arises from the spin, right? So one is the angular magnetic moment. If we are representing the magnetism in terms of how the magnetic field or the magnetism arises from in terms of quantum numbers, then the first one is the angular moment, angular magnetic moment, and the other one is spin magnetic moment. These are the two magnetic moments. Again, simplifying it in a classical manner. So angular magnetic moment arises from, let's suppose this is my nucleus, which has the protons and neutrons in it, and the electrons. The electron is revolving around it. For example, if I talk about the hydrogen atom, right? If the electron is moving, circulating around a nucleus, and because of that, if we apply the Biot-Savart's law, then we have the generation of magnetic field, right? Because of the movement of or the spinning of electrons. Now, another one is because the spin, the intrinsic spin of electron, right? So, which has electron is spinning in some direction. If I take in this direction, it is up, and if my electron is spinning in this direction, it is down. So it is plus half, it is minus half. Right? And the whole magnetism arises, and there is a magnetism. There is also this magnetic moment from neutrons, but it is very much low when compared to the spin magnetic moment and angular magnetic moment. Even the angular magnetic moment is very low when compared to spin magnetic moment. So the mostly in magnetism only the spin magnetic moment that dominates. So there is a magnetic moment from neutrons also. But that is few orders of low compared with the spin magnetic moment, so that can be easily neglected. Now, from the explained spins, right? The for example, if I am talking about from the spins, we arrive at different types of magnetic behavior of materials. Right? For example, we have paramagnetism. We have diamagnetism. And again we have ferromagnetism. This ferromagnetism. Antiferromagnetism. And another one is the band magnetism. So I will not go deep and derive everything. So in paramagnetism I will just tell you about why it is happening and few applications, right? So, for example, if you are talking about the diamagnetism is an inherent property of any material. So, every material is a diamagnetism. Every material exhibits diamagnetism, but its spins will cover or they just diminish the values of diamagnetism, and they have the prominent effect. For example, in paramagnetism, the paramagnetism, ferromagnetism, ferri and antiferro, these can be explained differently from the paramagnetism. In paramagnetism, we assume there is no interaction between spins. That's how we arrived to the Curie paramagnetism, right? So let's suppose you have a material and in that you have spins which are very randomly oriented, right? So these spins aren't interacting, and paramagnetism shows that on application of the magnetic field, these magnetic moments will show reaction with the magnetic field, and these moments will align themselves, and it has a poor response when compared to ferromagnetism, and in case of diamagnetism it repels the magnetic field. Like these magnetic moments will make sure to align in such a way that they show the opposite response, right? So they doesn't show a response like a paramagnetism. That goes for the diamagnetism. Now coming for the ferromagnetism arises from the spin-spin interaction. Right? For example, if I take the same material, in ferromagnetism we have the exchange interaction also. So again, what is exchange interaction? Let me write it. What is exchange interaction? So to understand what is exchange interaction, we have to know like 2 to 3 things, right? The first thing we need to know is the parity operator. The parity operator or time operator. And other one is the wave function, writing the wave function. For electron in atom. Let's say if I consider only the excited state of helium, right? Let's say if I take the excited state of helium, right, for example, this is my 1s, this is my 2s, 2p, right, I have 3 energy levels, right? So again, my electron, if one electron is here, my other electron can be here, or this is one state, this is another state, right? So that is all. Now if I write the wave function of electron 1, let's say first electron is at 100, that means 1 is my principal quantum number, 0 is my L, and another 0 is my ML, right? So azimuthal quantum number, right? And my next state is 2 L ml, and I don't know the L or ml because it can be in 2s orbital, it can be in 2p orbital, right? Divided plus the in other way, the first electron can be here, ml plus by root 2. Now convolution or multiplied with the another state. What is my other state? Which can be a singlet, right? What do we mean by singlet? Alpha, beta, beta, gamma. What does that mean? Now alpha is my spin magnetic moment, which shows the plus half, and beta shows minus half. So one electron which is in 1s orbital can be in up direction, and the other electron either it is in 2s or 2p, which can be in down direction. Or the first electron which is in either of the states in 2s or 2p, which is in up position, and another position, and other electron which is in 1s orbital, which is in down state. So that is my singlet. Now what can be my other wave function? The other wave function will be, why I mentioned the parity operator. What does parity operator do? Parity operator, it just, for example, if you are talking about bosons, the parity operator will just give a negative sign before the wave function, right? So the electrons are bosons, right? So either we can have a symmetric wave function or asymmetric spin states, right? With plus half and minus half. Or the wave function can be asymmetric wave function, the spatial distribution wave function, and the symmetric spin distribution. So those are the two cases. Let me represent it again. This is the states will be same. The electron will occupy one of the 1s or 2s or 2p. So but the only difference is this asymmetric spatial distribution. Now on solving this will give us the energy of a singlet. Now, on representing the 100 or the spatial wave function of an electron from the Schrodinger wave equation, we will finally arrive to this. Right. So, energy of a singlet will be equals to E square by 4 pi epsilon naught. I'm simplifying everything so that we need not to go to the whole calculation. This is R1 minus R2, the position of 2 electrons times symmetrical. Now same, if we write it for a triplet, this is asymmetrical, right? Same will come here and asymmetrical. So again, upon solving, the singlet will turn out to be, it will have two values. One is I and another is J. And for triplet, we have I and another one is J, but the values are different. Then they have different in energies. Now why there is a different in energies? Because of the splitting of the energy levels, right? So it will, if I show you on the graph, this is my energy, this is 1s, 2s, or 1s, 2p, right? So I have two things. If my electron is in 2p, if my electron is in 2s, right? So one goes for my singlet and another goes for my triplet. Now what is the difference? What is the difference in energy? I plus j minus of I minus j, that will be 2j. So this is my interaction energy, right? So And this is the reason, because we see, even upon measuring the energy of an electron in the states, why there is a difference in energy, because of this interaction energy. And this interaction energy is cannot be explained classically. It is a pure quantum mechanical thing. Okay, so interaction electron interaction energy arises from only the first we explain the parity operator. Then from parity operator we go to the how the spatial, if our spatial wave function is symmetrical, then our spin wave function should be asymmetrical. So that is how. And this interaction energy, exchange interaction energy plays a crucial role in understanding the ferromagnetism, and antiferromagnetism, right? So that is about the different types of magnetic material responses. Now, how the spins are there in the ferromagnetic material. In ferromagnetic material, this is my body, and if I take a domain, right? What are domains? Domains are nothing but, for example, if I take crystallite, and crystallite we say they are coherently scattering domain. Why we call it a coherently scattering domain? Because the scattering phenomena or the diffraction that we get from that particular crystal structure will be different when compared to other crystallites. So the same goes for the domain. So in this domain, all the magnetic moments are aligned in a specified direction, right? So for ferromagnetic material, it has a very strong response to for the applied magnetic field. In ferromagnetic material, even after removing our magnetic field, we still have a saturation magnetic field, or we call it as a coercivity. Not the coercivity, it is retentivity. So now for antiferromagnetism, in antiferromagnetism, there are equal spins but with opposite direction. So here the magnetic moment is not the total magnetization, or the total magnetic moment is not zero, but here it is zero, right? Because and this antiferromagnet shows no response to magnetic field, and this is for antiferromagnetism. Now ferromagnetic moment. In ferromagnetism, we have spins with equal and opposite directions, but the magnetic moments of each spin of the magnetic moments of spins in one direction is not equal to one another. Let me write it. So, for example, all the spins that are showing in upward direction, upspin is defined by A atoms, and the down spins are given by B atoms. Now the magnetic moment of each atom is, for example, is mu A, and for atom B is mu B. Then these two are not equal. Then we have antiferromagnetism, right? So coming to the application part. Now where do we use this? Now how do we create the magnetic field initially, right? So we create the magnetic field with the help of a solenoid. If this is our voltage source, right? This is our core and this is our solenoid. Now there is a creation of magnetic field. This is how the magnetic field is created with the help of solenoid. Right? So it is not. It is based on the Faraday law of induction. Right? If we have an current passing through a conductor, it creates a magnetic field around it. Right? So it creates magnetic field around it. So based on that Faraday law of induction, from the solenoid we can create the magnetic field. Now this magnetic field can be easily calculated, which is equals to B equals to mu naught N by L into I, where mu naught is the permittivity of free space, N is the number of turns, L is our length of the coil, and I is my current passing through. Right? Now what is permittivity? 8 I into 10 to the power of minus 4 pi. So this is how the magnetic field is created. Let me write it again. Mu N by L into I. I is in amperes, M is number of turns, L is in meters, and that will have a unit of Weber. This is B, and if you want to measure magnetic flux, this is equal to Weber per meter square, or the magnetic field intensity divided by the magnetic field induction divided by area. This is our magnetic fields. So that's all for today. So far we have discussed the thermal properties, electrical properties, and also bits and pieces about the magnetic properties of nanomaterials. So in the next session we will go through the magnetic properties along with the optical properties. So thank you. We'll meet in the next session.